Okay, we go on with the geometric system response evaluation. So the Fourier transform can be evaluated geometrically by considering the pole and zero vectors in z plane, considering the pole and poles and zero vectors in z plane. So let's do an example. What do you want to mean for this? This is a first order system, e to the z minus 1. And this is the region of convergence. It tells us that this is a right side sequence. So you know the Fourier transform of this system. Discrete Fourier transform of this system is simply so, as you remember, the z is r times e to the j omega. If you choose r, the magnitude of r is 1, so this will in this case equal to discrete Fourier transform of the system. So let's plot to z plane. This is imaginary, this is the real part. So for this system, as you see, h of z is equal to c over z minus a. So there is a 0 at origin. Oh, sorry. There is only 1 0 at origin and a pole at point A. So this is A, let's say. There's a pole at point A. So in order to draw the Fourier transform or evaluate the Fourier transform of this expression, we do something like this. Let's say this is the unit circle, okay? So this is r is equal to 1, let's say. And this is the point that you are, let's say, plotting, okay? So this is the omega. So this is the, let's say, magnitude response of your system, e to the j omega. So by choosing r is equal to 1, this is 1. So this is a unit circle, and if you evaluate your point in this circle, you will get the magnitude response. So you can do this geometrically. How can we do this? So draw the vectors from pole and zeros at the point omega. So what? Omega is, in this case, this frequency axis, okay? So as you remember, for discrete sequence, this is between pi and minus pi. So this is angle, let's say, for these are the vectors. This is v1 vector, and this is the v2 vector. This is the zero vector, and this is the pole vector. So v1 is the zero vector, v2 is the pole vector in this case. Okay, how you can draw by looking only this plot, and how can you draw the magnitude response of this sequence. So in order to draw this, we give two expressions. One is for magnitude response, and it is equal to let's say the pi is in here. The magnitude of V1 over to V2 over V2, okay? So this is magnitude of V1, this is magnitude of V2. And what about the angle? So in order to plot the Fourier transform, this is the magnitude response, and also there is an angle or phase response of this signal. So in this case, angle of V1, where is the angle of V1? This part is angle of V1, and this is the absolute or magnitude of V1 in this case. Angle of V1 minus V2, angle of vector V2. So let's try to draw the magnitude response of this system, okay? So you start from 0, this is for omega 0, and counterclockwise direction, and this part is pi in this case, and this is the minus pi part. So from 0, as you see, this will show the vectors, and the angles are 0 in this case, so the angle response is 0 at point 1 in here, and or omega 0, and if you increase omega, you will do these manipulations. So let's try to draw this for this A point. Let's say this A is 0.5, so it is at the half of this unit circle, and the other expression for A is equal to 0.95. So if you change the point of this, you will see the response actually. For A is equal to, let's say, 0.5. In this case, for 0 point, as you see, this point is close to the pole, so the vector V2, V1 over V2, but the distance is half in this case, so the response is something like this. From 0, omega 0, and omega pi point is in here. So this point is the I think the at this point you are very close to pole, and you are moving away from the pole by going into omega. So while moving away from the pole, as you see, the magnitude of V2 is increasing in this case if you move away from the pole, so this magnitude response will decrease in this case. So what about if A is, in this case, A is equal to 0.5? What about if A is 0.95? In this case, you're moving this pole close to unit circle, okay? So the distance of V2 is decreasing. In this case, close to 0. So something over close to 0 means a huge number. In this case, at point 0, for A is equal to 0.9, this expression will give a huge value. So in this case, it is a bigger value in this case, okay? So by going this counterclockwise, or by going moving away from this pole and going to through P, this V2 vector is in this case increasing, the length of this V2 vector is increasing, and the overall magnitude response will decrease in this case. So it is something like this. For A is equal to 0.95. For the other part, it is in this case symmetric, and same things. I'm sorry. So this is symmetric. So if you if you put this pole, or if you increase the value of A, and if this is closing to the unit circle, this will be more sharper. So the sharper increase. If A comes to 1. In this case, as you see, you're starting to plot your Fourier transform from this point. This is the 0 point, and from the counterclockwise. And in this point for 0.9, you are close to pole, so it will give a huge value. And if you go through pi, move away from the pole, this value will increase in this case. So this is the magnitude response of this system. What about the phase response? So this is the expression. So you are subtracting the angle of V1, which is the zeros vector, the angle of pole, V2 in this case. Sorry?
I'm not sure why they can check
Sorry?
They can check
yeah, sure. Of course. Thank you for this. I think there are some Java applets in website, so please check. You can add some zeros and poles into Z-plane, and then you can check how the Fourier transform, magnitude Fourier transform is in this case changing with the positions of these zeros and poles, and maybe you can change the position of this pole and see what is the magnitude response is changing in this case. So for the, let's say, phase response, so let's say this is the phase response, minus pi to pi. So this is for A is 0.5, for A is 0.95, and this is the magnitude phase response in this case. This part is important. Maybe in your final examination you will see such a Z-plane, and then someone asks you if the zeros or poles are in this position, what will be the Fourier transform or magnitude response of your Fourier transform or phase response. So you can you should match these and by looking only this Z-plane. Okay. Another example for this. So there is a Z-plane. Let's say there is a double zero at the origin, and there are two poles at these points. This is theta 1. The angle of these poles are theta 1, and the distance of these poles are simply r. Okay. So this is the, let's say, unit circle, and let's say this is point omega. So you're going from 0 to pi counterclockwise direction. And these are the vectors. This is a pole vector, this is another pole vector, and this is the zero vector, but there is a double zero at the origin. In this case, we call this zero vector as V1, and this is the pole vector V2, this is the other pole vector V3. So this is first order system, and there is a single pole in this case, but in this system there is two poles, so this is a second order system. Okay, let's draw the magnitude response of these pole zeros. So what is this? So this is the length of your zero vector. So square of this, because there is two zeros at the origin. And what about the poles? Poles are V2, V3. So multiply these two vectors in order to find the magnitude response. Let's try to plot simply the magnitude response of these poles and zeros. This is a geometric evaluation in this case. This is omega plane, this is pi, and this is minus pi. As you see, for this point, we are close to poles, and if you go here, in this case, you close this pole, okay? So from, let's say this is theta, at point theta, you are close this pole, and this will give you a, let's say, increase or a peak at this point. By going this, you are moving away from this pole, and at this point, the effect of poles is minimum in this case because you are far away from these two poles. You are, in this case, at this point, you are close to, let's say, double zeros at this point than these poles. So, in this case, it is decreasing. What about if you go in this way from 0 to minus pi? In this case, at theta 1 point, you are very close to this pole, and again, let's say this is theta minus theta. So you will have a peak in this at this point, and after this will decrease. Okay. If you, let's say, increase the r, so if you make these poles close to unit circle, let's say you move these poles, if you move these poles close to unit circle, let's say in here, the green ones, so you change the position of these poles. In this case, they are more close to unit circle, and your Fourier transform will be in this form in this case, if these are more close to unit circle. Okay. So I advise you to look to Java applets in website and change the positions of zeros and poles and see what is the Fourier transform change in this case. So we come with the properties of the inverse Z transform. So you see the properties of inverse Laplace transforms or transform pairs. In this case, we will do this for the Z transform. So the properties of the Z transform. So the white color is good. The first property is linearity. So Z transform is a linear transformation. And since this is a discrete sequence, let's say you have two x1n and x2n. So the Z transform of x1n is x1z. Let's say it is given in this case. So what about the region of convergence for this? It is R1. It is a region and it is given to us. So this R1 specifies a region in Z plane. Okay. What about x2n? The Z transform of x2n is x2z, and it is region of convergence is specified as R2. Sorry. So if you add these two terms and multiply or scale these sequences, And if you take the z transform of this scaled and multiplied sequence, since this is a linear transformation, it's simply a times x1 z plus b times x2 z. What about the region of convergence of these sequence? So in this case, a new region of convergence is the intersection of these two regions. Okay. So this property is, I think, clear. The other one is time shift. Let's say the Fourier transform of xn is x of z, and if your sequence is time shifted with n0, in this case, what about the Fourier transform of this is z to the minus n0 x of z. So it is also given that x of n, the z transform of this is x of z with the region of convergence R. Okay, so this is given. So in this case, if you make a time shift of your sequence, so your Fourier transform is in this case this. And what about the region of convergence? It is again R, of course. Region of convergence will not change, but of course there can be some addition or deletion of infinity. Since we multiply or z transform with z to the minus n0, we put n0 poles in this case, as you see. Let's write this. Can write into here. There are some important points for the region of convergence of this expression. Since we multiply the x of z with this term, since we multiply by n0, in this case we put n0 poles, because the order of this is n0, whatever n0 is. If n0 is greater than 0, at z is equal to 0. So we add some poles at the origin, n0 poles in this case. Of course, there can be some zeros at the origin. So if there is some zeros at the origin, in this case, there is a cancellation. So which can cancel zeros at z is equal to 0. So if there is some zeros at the origin, by doing this operation, you can cancel these zeros at the origin. Or let's say if n0 is less than 0, okay, so in this case we put zeros. Of course, which can this time cancels poles. You should check the x of z and the region of convergence of this transformation. So the poles or zeros are in this case changing by this way according to pole zeros of x of z. Cancels poles. For the first case, what is the first case? In this case, the n0 is greater than 0, so you're adding some poles at the origin. For the first case, we may remove origin from the region of convergence. But for the second case, in this case n0 is less than 0, and in this case you are adding some zeros. We can put origin into region of convergence. So as you see, the region of convergence is same, but you can add or delete some poles or zeros according to your poles and zeros of x of z. Okay, this is the time shift property. So the third property is scaling in z domain. This is time shift property, but in this case you multiply xn with z0n. So what about the z transform of this? It's x times z over z0. So how the region of convergence are affected from this operation? So in this case, the region of convergence is z0, magnitude of z0 times r. So what? This is the, in this case, scaled version of the previous region of convergence r. So by doing this operation, let's say that this is a special case for this. Let's assume that z0 is e to the j omega 0. Okay? This is a special case. And you take z0 as e to the j omega 0. And in this case, you're multiplying e to j omega 0 xn. So this is your sequence, and you're multiplying your sequence with a complex exponential, ej omega 0. Times n, of course. Okay, so you do this operation in this way. If you take z0 as this one, this is a special case because we took in this r1. So in this case, this is we can do this in Fourier domain. So what is the Fourier transform of this sequence if you multiply this with this? So this is the Fourier transform of this sequence. So there is a multiplication with a complex exponential in time domain. What about in frequency domain? In this case, this is a rotation. Or in what about in z domain? This is a rotation in z domain. What do you mean with this? Let's say they assume there is a term let's say x of z is this, and you multiply, let's say, the time sequence, the inverse sequence of this with this complex exponential. In this case, what about in z domain? What is the effect of this in z domain? As we have specified, this is a rotation. So what is the effect of this? Let's say this is the pole zero plot of your sequence x of z, and after this operation, if you multiply this with z0n, or in this case e to the j omega 0n, this will be a rotation in z plane. What kind of rotation is this? In this case, let's say this is omega 0. So this is theta, the original sequence, and this is omega 0. So the overall angle is theta plus omega 0, and this is the r. So it not change in this case, and this is the position of to 0 after this rotation. This is the z plane. So after this multiplication in time domain with a complex exponential, in z domain there is a rotation with this specified angle omega 0. Okay. Other important property is time reversal. What do you mean with time reversing? X minus n. So you reverse your sequence. What about Fourier transform? If you reverse your sequence, it is 1 over z in this case, or xz to the minus 1. So if you know the Fourier transform of x of n, let's say xn, the Fourier transform of z transform of x of n is x of z, and if you reverse this time sequence, and then the Fourier transform is in this case put z to the z minus 1 instead of z, and find the Fourier transform z transform of this time reversed sequence. So what about region of convergence? How a region of, let's say the region of convergence of this sequence is R in this case. If you reverse your sequence in time domain, and then what about the region of convergence of this reversed sequence in Z domain? So the region of convergence is in this case 1 over r. So what do you mean with 1 over r? Sorry? Yes, sure. Right, this is in this case complementation. So let's give an example. If Z0 is in rock region of convergence of Xn, let's say there is a Z0 in regional convergence of Xn, and if you make this time reversion, in this case 1 over Z0 is in the regional convergence of X minus n. As you see, all the poles are zeros are converted or complemented, or 1 over Z0, as you see. If it is Z0, it will be 1 over Z0. The other important property is time expansion. So we make a definition now. X, there is a sub-index k, in this case, n. So what do you mean with this? It is X n over k, okay, 0. Let's explain what's the meaning of this. So as you know, if you sample a sequence, if this is a discrete sequence in this case, these should be integer, n over k should be integer. Let's say if you do this operation, let's say if k is 4, in this case you're adding some extra samples into your sequence, okay? So why this is a time expansion in this case. So for this, by doing this, you're adding some extra samples into your sequence. So the meaning of this is add some k minus 1 zeros inserted between successive values of the original values of the original sequence, okay, or signal. So you are expanding your sequence. Maybe you increase your sampling rate and you're adding some extra samples instead the original signal. In this case, if you take the z transform of this, it is xz to the k. So what about the region of convergence? The region of convergence is in this case r 1 over k. Let's say if A is a point in Z plane, and if this point is in the region of convergence of your original sequence, let's say Xn, then A over 1 over k, A 1 over k is in the rock of xk of n. So you have an original sequence and xkn is the expanded version of this. And as you see, this is the Z transform of this expanded version. So the region of convergence in this case are 1 over K. So if A is a point in Z plane, A 1 over K is in the rank of the expanded sequence. So this is the time expansion property. Another important property is the conjugate property. So let's say if you have a complex sequence, in this case x of n, what about the Z transform of this x of z? And the region of convergence is R. So if you take the conjugate of this sequence, what about the Fourier transform? In this case, it is Z conjugate okay, and the region of convergence is again R. You can do this, or you can prove this using the definition of Z transform. X of z is equal to z to the minus n. So by taking the conjugate of this sequence x conjugate n, you will see in order to find the conjugate of this sequence, you should take the Z conjugate of this signal in order to reach the Fourier transform or Z transform of this sequence. You can check this. So this is the sixth property. Another important property is the convolution. So if you let's say you are convolving two sequences, discrete sequences, or signals, discrete signals. So the Fourier transform of this is multiplication, convolution in time domain, multiplication in frequency domain. So in Z domain, the same thing. In Z domain, it is same. So it is multiplication of the Z transforms of these two sequences. What about the region of convergence in this case? The region of convergence is, in this case, the intersection of these two sequences in regional convergences. So R1 intersection R2, let's say. The regional convergence of this is R1 and the other one is R2. So if you convolve these two signals, you multiply the Z transforms and the regional convergence is this. Let's do an example. Let's assume you have a linear time invariant system, and the output of your linear time invariant system is y of n, and the input is x of n, and hn is your impulse response in this case. So in this example, your impulse response is given delta n minus 1. Okay, this is your impulse response, and what about h of z? for this sequence, for this system. It is 1 minus z to the minus 1. We have seen this in previous lecture. So what is the output linear time systems z transform in this case? This is y of z. Okay. So it's simply, you know the h of z, it is 1 minus z to the minus 1, multiply with the z transform of the input sequence. So this is your output z transform. So what about this? As you see, this is z minus 1 over z. So there is a pole at z is equal to 1. Oh, sorry, z is equal to 0. There is a 0 at z is equal to 1. Okay. So by multiplying the input signal z transform with this 1 minus z to the minus 1, we insert a pole at origin at 0 or remove a 0 from origin, and we insert a 0 at 1. In this case, we insert a 0 at 1. If there is a pole at point 1, we remove, in this case, this pole. So this is a differentiation operation, the first order difference. The meaning of this is first order difference. So with this system, there is a system with h of z, and in this case this is h of z. You are differentiating the input signal with this filter. Okay, this is the system response. With this system, you're taking the first order difference of input signal. So this is also a differentiation property. As you see, the region of convergence is changing in this way. You're adding a pole at the origin and adding a 0 at z is equal to 1. What about integration? So this is a differentiation system. Maybe you can put an integration system. So this example is related with integration. Let's say the output of integration system is Wn in this case. So it is equal to add all the previous values of input signal. So this is integration in time domain. So what is the expression of this? It is simply convolution with step response with the input sequence. If you convolve with input signal x of n with the step response, you add all the previous values of the input signal, and this means that this is integration in this case. Sorry? Sorry, you are right, you are right. I'm sorry for this. So we changed the index. So n is in here. So k is start from minus infinity to n, because you are integrating at point n. Okay. So all the previous values, and it will reach through to n, point n. So this is the un convolve with xn. What about the z transform of this? As you know, the z transform of this is the z transform of this sequence. This is the step response. What is the z transform of this step response? It is 1 over simply 1 minus z to the minus 1, right? And multiply this with x of z. So this is the integration. As you see, you are inserting a pole at z is equal to 1. So insert a pole at z is equal to 1, insert a 0 at z is equal to 0 by doing this operation. As you see, this is the differentiation and this is the integration system. So the last property, the eighth property is differentiation in Z domain. Okay. The one important thing is the regional convergence in this case. So the rock will not change and it is still R. So the initial value theorem, I want to talk on this also. Initial value theorem. If your input sequence xn is equal to 0 for n less than 0, in this case we can say that the initial value of your sequence x0 is simply so this is the initial value theorem. Why? So let's write the Fourier transform. It starts from 0, this sequence starts from 0 to infinity, x of n, z of n. What? This is x of z, as you know. So if z goes to infinity, it will, we can say that this is the initial value. So z to the minus n is 1 for n is equal to 0, and z to the minus n is 0 for n is n is greater than 0 if z approaches to infinity. So initial value theorem tells us that if your sequence is a positive sequence, or there is no value for minus indexes, in this case the x0 is equal to this. So after, I think we have no time, so we will talk about discrete linear time invariant systems and causality and stability properties. Then finally the block diagrams for the, I think, Tuesday. Yeah, right, tomorrow. Okay, see you.